Hi, this is Professor Fernandez, and we're doing class notes D from lesson 3. So let's see what's going on here. The first thing we're asked to do is to verify that e to the t and e to the minus t are solutions to this solved. So that we can do without too much trouble. So what we're going to do is take each of these functions, substitute them into here, and verify that when we combine them in that way, we get 0. So the first thing we'll do is y1 equals e to the t. And if we are going to substitute it into this left-hand side, then we are asked to find the second derivative of e to the t and then subtract e to the t. It just so happens that e to the t's derivative is e to the t. And then you differentiate that again, you get e to the t once again. So we get e to the t minus e to the t equals 0. So check. That means that this function solves the solved up here. So that is how you verify it. And then let's do the same thing now for y2 is e to the minus t. This will be slightly different because of that negative t up there, but this is just a small application of the chain rule. So the first derivative of e to the minus t is negative e to the minus t. And then we got to differentiate that again. And then that brings down another one of these negatives to make it positive e to the minus t. So this up here, second derivative of e to the minus t is e to the minus t. And then we subtract the e to the minus t from this second term, and once again we get 0. So indeed, these two functions solve the solved up here. So that's great. And then the rest of the problem is basically trying to use all this information to find the unique solution that we think is going to exist once these initial conditions are applied. Introduced into the problem. So let's look at number 2, calculate this thing. So what is this thing? Let's scroll up a little bit so we can talk about it. So this thing, the notation up here from the definition up here is the Wronskian. So here is the first place where that notation showed up. And what is the Wronskian? So if you have covered some linear algebra, then this might make sense. As I say here, this is not something that I think you're going to necessarily know at this point in the course. We'll do a lot more linear algebra later. So the definition that I'm going to go with is the actual thing in the box that says definition, which is this thing over here. So this is the Wronskian. So if I take two functions, two solutions of a homogeneous solved, their Wronskian is this particular combination of them. Find the derivative of the second function here, multiplied by the first function, and then subtract the product of the derivative of the first function here with the second function there. So it's a very sort of algorithmic thing to find. So I'm going to scroll down here and apply that definition to the two functions in this problem. So here we are. We're going to calculate the Wronskian. y1 up here was e to the t, and y2 was e to the minus t. So e to the t, e to the minus t. And remember, the Wronskian says y1 y2 prime minus y1 prime y2. Great. And then I'm going to calculate this. So the derivative of e to the minus t is negative e to the minus t. And then over here I have derivative of e to the t, that's just e to the t times e to the minus t. So this gives me negative e to the t minus t, that's 0. E to the 0 is 1, so I just get negative 1, minus, and then here I get e to the t times e to the minus t, same thing. So I have the same base here. I add the exponents, t minus t is 0, e to the 0 is 1, so I get negative 2. So this is my Wronskian. Okay, so that's part 2, and then part 3 says, based on your work thus far, are y1 and y2 fundamental solutions? Why or why not? So let's scroll up a little bit, figure out what those fundamental solutions are. So that's in this definition. So fundamental solution. So what are they? Well, whenever solutions to a homogeneous solved satisfy non-zero Wronskian, they are called fundamental solutions. So all we have to do is check whether the Wronskian we obtained is 0 or not, and that will tell us fundamental solutions or not. Indeed, so we got a non-zero Wronskian. It doesn't really matter that it's negative. That actually doesn't tell you much. What matters for fundamental solutions is that it is non-zero, yes, because the Wronskian of these two solutions is not equal to 0. Right, so that's our answer for 3. Then we're going back up here and looking at number 4. It says, suppose that we impose these initial conditions, prove using the theorem that a unique solution exists on the entire real interval. Okay, so I won't scroll up again to remind you of the theorem. I did that in the previous 2 videos. But remember, this theorem has a few requirements. The first one is that we're talking about a solved. We are. Second one is that we're talking about homogeneous solved. We are. The third one is that there are initial conditions given. There are. And then the fourth one is that the P of t and the Q of t functions in the solved are continuous on the interval containing the t value of the initial conditions. Okay, so the standard form, remember, for a solved is this, for a homogeneous one at least. So if we compare these two, P of t here is 0 because there is no y prime term there. And Q of t here is -1 because that is what is multiplying y. So this is a really, really nice solved as far as using this, employing this theorem is concerned, because P of t and Q of t are both numbers. Sorry, I pressed a button and it took me all the way to future lessons that you'll see in future videos. So as we were saying here, P of t and Q of t are both numbers, so that means that they are automatically continuous everywhere. And that's one of the reasons why the interval for this problem is, all real numbers. Great, so I've just verbally talked through the fact that the theorem that we are asked to use here, in fact, applies. So I won't write much down here. I'll put here, listen to the last minute of this video. And by last, I mean, not the actual last minute of the video, but the last minute that I've been talking. Okay, great. So let's go up here and talk about number 5. Finally, find that unique solution, right? The theorem tells us that we know a unique solution exists. There must be one. How do we find that unique solution? We are going to apply the same procedure that we applied in the previous example in this lesson, and the same approach. We are going to say, well, to find that solution, I know from theorem 3.1.2 that y of t equals the linear combination of the 2 known solutions. They're given to us here. We verified that they're solutions in part 1. We're going to say that this is another solution. Okay, great. That is another solution to the ODE. So we are then going to start applying the initial conditions. So what are they in this problem? So y of 0 equals 0, y prime of 0 equals 1. Okay, great. So y of 0 is 0, y prime of 0 is 1. And so if I put in t equals 0 here, and I put in t equals 0 here, I get 1 both times. So this is c1 plus c2. And then if I take the derivative, nothing's going to happen here, and a -1 is going to come down here. So when I put in t equals 0 after taking the derivative, I'm going to get c1 minus c2. Again, that minus sign is coming from differentiating that and getting -1. So I am left solving this system. The easiest thing to do here is just to add the 2 equations, because then the c2 terms will cancel out, and I will get 2c1 equals 1. So c1 equals 1/2. And then, as what happened before, c1 plus c2 equals 0. It means that c1 and c2 are just the opposite signs of each other. So this implies that c2 equals minus 1/2. So our final answer for the y of t function is 1/2 e to the t minus 1/2 e to the minus t. And again, this is a function that solves the initial value problem. And we had already proven in the part 4 here that there was only one solution to the initial value, to this initial value problem that we're considering. So we're done. This must be the one and only solution. All right, so that's it. Thank you.